Hi. I'm going to talk to you all a little bit about the work that we're doing at Boston Dynamics, show you some of our recent results and some things that we haven't quite shown in the public yet. And then also, as part of that, call out places that we're using ML and computer vision, since that's the topic of the conference, and give you a little insight into things that happen behind the scenes inside of our robots. I've been at Boston Dynamics for a long time, and it's been tremendously gratifying to see our robots graduate from working in the lab and being research machines to being machines that are used by actual customers in the real world. And we'll talk a little bit about those applications and the way that it's a platform that can allow people to get their ML work and their computer vision work out into use by others. So at Boston Dynamics, we think of ourselves as actually being on quite a long-term mission. We're not just out to make a buck. Well, we kind of are, but we also really want to change the world by building machines that eventually reach the capabilities of humans and animals, right? So we mean that in the athletic sense, right? They can move throughout the world. We mean that in terms of what they can do, right? That they'd be able to manipulate things, that they'd be able to make decisions on their own. And then we want those machines to go out and be a part of everyone's lives before they reach some impossible pinnacle, right? But instead now, and hopefully enrich things, right? Be a positive impact on humanity and the people there. And I think the fact that we have that long-term vision is what's let us keep focus over the years on what we're doing and continue to sort of innovate in many ways and to deliver like new capabilities beyond just what we achieved the year before. So we really have 3 product lines right now that we're actively working on. Atlas on the far side is more of a research product. We'll talk about that in a second. But Spot is a product that you can go out and buy right now, right? You can call up sales and they'll ship you one in a box. It is designed to be a general purpose robot, but in many cases we think that it's very useful for autonomous data collection and inspection, particularly in facilities like warehouses and in places that are factories, power stations, etc. And we'll show some video of that in a second. The other thing that's cool about Spot is it comes with a wide variety of payloads and built-in capabilities, so you can program a mission and have it traverse your space. You can buy various cameras and attachments, and then you can also get an ARM and computing platform, which allow you to place your own software on the robot and control it through an API. Where Spot's designed for general use in the world, Stretch is really targeted and evolved for one particular location, and that's the material handling warehouse. And we think that Stretch allows us to automate a variety of tasks that happen in that environment in a way that will help people get more done and also offload a kind of work that is very, very physically demanding for people. And so this robot is able to use its arm to unload boxes, in this case from a truck or shipping container, and place them onto a conveyor. And we also think it's adaptable to a variety of other logistics activities. And this is in production now, and we'll be shipping units very soon. And then on the far right is Atlas, our humanoid robot, and it's really targeted at research, right? We want to, we're not going to sell this anytime soon, but we want to push the envelope of what robots can do and also explore spaces like manipulation. All of these systems ship with vision on board. So for example, Spot carries on it 5 RGB cameras along with full sort of stereo vision depth sensing around the robot, and you can buy additional sensing. Stretch has a sensor mast that's attached to the back of the robot, which is custom designed to allow us to take imagery and depth information about that wall of boxes and then use that in a machine learning algorithm. And then Atlas ships with an RGB D array in its head, which gives it information about the world in front of it. Spot is our product line. It's not all work and no play. Here, this is the robot doing a dance to a song by BTS, a very popular K-pop band. And we think this work is really exciting. It shows robots really positive points. People really resonate with it. Technical folks like ourselves, and to program these sorts of fluid, like relaxed motions in a robot, right? A lot of work goes into that. And thirdly, we take these kinds of capabilities and package them up and make them available to our customers. So we actually have customers that are able to use pieces of the Choreographer API that this is all based on, and they're able to build their own dance moves. In this video, we're showing Atlas in our lab space just up the street from here in Waltham. And it's doing a variety of athletic maneuvers, and this is in the vein of approaching human capability. In fact, in this video, there are things here that I can't do personally. And so you can see what this is really just a great deal of whole body coordination, the ability to synchronize where it's moving so that it's able to work in constricted spaces, choose the footsteps that it needs to use, and all that's based on computer vision being run through a variety of algorithms. What's interesting here isn't, I think, how much is working, but it's actually how far we still have to go, right? Behind the scenes, the thing that you don't know is that a human being was involved in designing when and where it needs to do all of its moves, right? And telling it, this is where you backflip. This is going to be a staircase coming up. You'll probably need to switch to this gate in order to run over it. And so although our vision system in this robot is capable of telling it all sorts of things about what's coming in front of it, it still relies on a human to help it understand the wider environment. And I think that's a challenge for robotics moving forward, right? To be able to have the robot be able to look at the course and design its own motion through it, or understand that it's trying to do a dance and find a way to make its own moves for those dances. Here's a little bit about what happens inside of our stretch robot. So again, this is our logistics and material handling robot. And what you're seeing in this video is the robot's eye view of the world in some sense. And this is taken right out of our internal tools that our engineers use to develop behaviors. So in the center of the screen is the robot's understanding of how it's positioned in itself, right? So it can understand where all of its arms are, what it's gripping. It keeps track of the box, whether or not it can see it there. As the robot moves around, you can also see there's a conveyor in gray here, which is where it's trying to land the boxes that's attached to the robot. And then there's also an understanding of the truck wall and ceiling. I'm going to just back this up. Hopefully this will work. And play it again. There we go. The robot's able to take depth and distance data using the mast, and then it uses ML-based algorithms over here on the right to recognize boxes. And that's actually a really hard problem, and we've been very happy with the performance that doing deep learning and neural networks has provided there. And then based on that information, it's able to make a set of hypotheses about where boxes are and strategically pick the next box to offload. And then it plans a set of arm motions that allow it to smoothly drop that box on the platform. And so all of this has to work together in order to make this robot able to unload a truck of boxes that may come in a variety of shapes and sizes, scrambled together, often of different weights and masses. And we'll show a video of it doing this sort of end-to-end in just a minute. But other than moving just boxes, we think manipulation's a new frontier, right? We think it's essentially the next place to be going with our set of robots. So in this video, you're watching the Spot robot move through an environment and execute a series of manipulation behaviors that allow it to control a switch and to open a door. And part of the way it's doing it is to use the sensing set that's around the robot, those stereo cameras I talked about, but also the arm contains both an RGB camera and a depth sensor that allows it to take sort of precision information and figure out where to reach. That all mixes together into a behavior that allows the robot to coordinate motions and then open the door. I think this is a really interesting space, particularly for people in computer vision and ML. A lot of Boston Dynamics' early work on locomotion was done on blind robots. Our first robots couldn't see the ground at all. They could only feel, and they would walk around. And over time, we built and added the ability to understand the shape of the world around you, that you're going towards a staircase, those sorts of things. On manipulation, you can't really start blind, right? In order to make those behaviors succeed, the robot needs to reach and grab the door the first time, right? It can't reach and miss the object and knock it on the floor. And so we're really much more sensitive to needing to be able to make really good understanding of the world around the robot and understand positions that are very fine and location of objects. And we really need ML to be able to tell us things like, hey, this is the object that you need to grab. So this is a little bit about how we see Spot being used by our customers. So these are a representation in these pictures of a factory, for example, it's doing some kind of work, and the sites of today and the right side cartoon are essentially places that are overseen by humans. Humans move through the factory, they inspect machinery, they try to understand whether things are breaking down, working correctly, and the end result is oftentimes that the site may have unplanned downtime, which ends up being very expensive. We think the sites of tomorrow involve a robot moving autonomously through the environment on a set of missions, and that by doing so, it will be able to capture information in a repeatable and reliable way all throughout that environment using a variety of sensors. So this is a quick video that shows sort of that idea being done at a variety of customer sites. This first part is, sort of a story piece about needing to do an inspection to understand what's on a gauge. And the better way is having a Spot robot on a dock that's able to undock and then be remote operated and move through a variety of different complicated terrain that you might find in a modern industrial site, open staircases, outdoors, and then use a set of sensor payloads. Some of these are built by us, some of these have been built by customers. It's very easy to build and integrate one in order to collect information that's specific to the task at hand. And the robot can go places that it's hard for a wheeled vehicle to go. Really having the ability to walk means that it's very well adapted to human environments. In that video there, you saw it capture a fire extinguisher and use an ML system that's mounted on the back to classify it. And then here you can see people using interfaces we've built and that our customers have built in order to understand and study the environment around the robot. And what's really exciting about this is you can just buy Spot and deploy it in many ways, right? And we're actively working with a set of customers that have deployed it in their environments, and we're working to customize how it behaves and make sure that it's able to do the tasks that they need. So zooming in on this is just a little bit, right? And I think this piece may be especially interesting to folks who work in ML and computer vision. These are the sorts of things that we've used Spot for, right? So for example, the robot can go around and take images of gauges from certain locations and then run those gauges through an ML algorithm and extract the gauge reading, right? This saves a lot of effort if you need to monitor a facility with a lot of legacy gauge work, and it's also an interesting application for ML. You don't necessarily need to just use cameras though, right? You can buy a payload that contains a thermal inspection system, and here you can see the thermal inspection system has found a hot spot in this area that is part of a power substation that wouldn't be a location that a human's allowed to go while the system's energized. And that hotspot might be an early example of a problem, and that in turn could prevent having to bring that power substation down in the future. We can also mount things like acoustic sensors on the back of the robot and detect noise anomalies. It turns out this is a really valuable and useful way to understand if machinery is starting to break down or behave in a non-standard way. And then finally, you can mount a laser scanner and go and create a 3D model or digital twin of your site and use that as part of your site planning and logistics. In this video, you can see Stretch performing end-to-end the sort of targeted behavior of unloading a trucker container. So one thing to take away from this is that there are a lot of boxes in these containers, and this is a repetitive task that honestly is not a lot of fun for humans to have to do. These boxes are not light, right? And the robot is able to handle them in a variety of locations and configurations, so particularly that center row there. As the robot moves in and out, it's able to bring the conveyor with it, and it can enter the truck, unload the boxes, and then pull the conveyor out there. Clear here is the kind of reliability that you need to enter the real world, particularly with regards to the machine learning detector, right? The goal is to have a robot move thousands of these boxes in a period of time, and that means that the kind of, you can't really tolerate a detector that has a mistake on every 1,000th box because you don't want to drop the box. If you do drop it, you can pick it up again using the robot. But that sort of gives a rough feel for the end-to-end view of how you could use that ML capability in our robots. And then finally, this is a bit about what we're working on next. So in this video, you see our Atlas robot. It has the RGB D-ray in the head. This is some live information from that robot. And we're working on coordinating a variety of the things we've just talked about in order to ensure that we can do tasks that are common tasks that humans might do in a factory or like a construction setting, for example. So just backing this up. Oh, hang on. There we go. And so the robot is able to use its vision system and machine learning to locate the object and determine a set of grasps on that object. It plans a set of footholds that allow it to find where that object is. It coordinates whole body motion in order to pick up the object. The object itself is heavy, and so it changes the dynamics of the system, and the robot's controllers adapt to that. And then it's able to drop the object and go back to balancing itself in the right way. And so you can imagine that if instead of a barbell, which is peak athletic performance in some sense, it were instead a component or a part that you needed to go and put in location, how valuable this sort of behavior would be. And this is an active area of work for us. We have teams pushing on this and a variety of related activities on the biped robots today. And that's just a quick summary of some of the recent work we're doing and a bit of a view of how ML and computer vision play into that work. Thanks for listening, and please let me know if you have any questions. Yeah, that's a great question. I was also pleased. So in order to achieve the vision we outlined at the beginning, in which robots, general purpose robots, are able to have positive impact on humanity, I think it's really important that the way those robots be used be exemplary of the kind of impact that you want, right? You want people to accept them and trust them and believe that they can work in the environment that, you can work alongside one of these robots one day. And so to that end, I think that the decision makes a lot of sense from the perspective of us trying to build world-changing robots and follow the vision that we have. There's a lot of internal conversation about how robots can be used, for good, and also things that we want to ethically be sure that robots are not used for. When you purchase the Spot robot, for example, the licensing that you sign does outline things that we don't want people to do with our robots, and we think that's a very important aspect also of how we work with others. And so in general, we also have a member of council inside the company who's actively engaged with a wide variety of policy questions like this, and he was one of the people who helped guide that. And we were really happy that so many other robotics companies were also willing to come together with us to help push that letter forward. Yeah. So, one thing to keep in mind is that DARPA funding funds all sorts of technology, right? And our experiences with DARPA have always been excellent, right? And so in that sense, GPS, the internet, all of these things came out of DARPA research. And so it's just a common funding mechanism. I don't think there's anything that necessarily made it particularly military oriented for us, so. Yeah, that's a great question. We maintain active communication with many of the customers, right? And so we, understand their applications and sell them to those customers, right? There's some licensing and components there. And we have some technical mechanisms as well that are available. They are a general purpose tool. And so in many ways, within what we say in the licenses, which is they shouldn't be used to harm robots, other people, animals, and shouldn't look like they're doing that either. That's stuff we take very seriously with the customers, and that's worked so far with us. Yeah, maybe it should be. The ethics discussions are pretty wide-ranging. I'd feel like the laws of robotics actually, other than being incredibly difficult to implement, are maybe just the beginning of the kinds of things that people talk about when they talk about how to ensure that the machines we build have positive impact for humanity. Yeah, absolutely. I think it's incredibly gratifying to me. I worked on the early big dog robots. And so those were these loud hydraulic machines designed only to work outdoors. We only owned a couple of them. And at the time, they were, I would like to think, pretty novel, right? People reacted very positively to them when we first showed video of them. To imagine that you can go now and purchase one of them in a box, a thing that really performs 100 times better than Big Dog ever did, right? Purchase it in a box. It's able to do things that, I think are really impressive from a technical perspective, like climb stairs, open doors, pick up objects, and that it's the kind of thing that customers are able to build software and applications on top of, right? That you as machine learning experts could build a machine learning system and land it on this robot and kind of get a head start on that. I think all that's really incredible to me to look at it from here. And if I look also at, I don't work directly on, for example, the biped robots, but just the kind of work the teams that do work on that do are, I think, astounding, even though I see it every day. And so for me, I'm very happy with what we've achieved over 20 years. So that's a great question. We did move to working from home, right? And that actually was a relatively smooth transition. I, for a while, had one of these robots in my house along with many of the other staff, one of the advantages of making a product. And there were some opportunities too. One of our customer-facing teams was able to do a variety of work with having the robots help in like some of the medical areas around the pandemic. And so there were some chances to do good as well in that situation. And so that was good. And now we're essentially back to business as usual, right? The office is full and people can get hands-on again in an easier way. And so I'm happy that we're back to that. Yeah, that's a good question. For the product robots like Spot, right, you end up essentially having to synchronize a set of engineering change orders that go out to a factory and say, hey, start producing cameras with, for example, RGB sensors in them now instead of black and white. That's an upgrade. And then you have to sync that up with a software release schedule where you have that along with all the other software you're going to release available on a certain date. Right, and that's a pretty common thing for software engineers to be like, hey, we have to ship now, and this stuff's going to go in, this stuff's not going to go in. For our more research-oriented robots, it's a very similar thing where we're coordinating the hardware and the software together and with the same sort of scheduling. It's just much faster, right? Because you don't have a factory, and instead you'd be like, hey, let's go ahead and try out this new, adding this new sensor. And then you'd be like, how quickly can we land software and that sensor in place and make sure that we have the bits in so that we support the old version or a robot without that sensor as well. And one of the great things about Boston Dynamics has been how tightly different domains of engineering works together. So, I work incredibly closely with electrical engineers and mechanical engineers in order to get my day-to-day job done, as does my team. And you can very quickly move from group to group, and there's a lot of respect among the groups for the kind of work that each group does. And so that's, I think, really the secret to that kind of teamwork. But like the project manager in me says, well, it's schedules, right? Joint scheduling and milestones. So. Super. Hey, thanks a lot.